Hello, so this video is part two of the limit techniques. We've already gone through the first four, so we've got three more to go for a total of seven limit techniques. And this first technique that we're going to look at now has to do with trig functions. So a couple things that you may need to brush up on if you haven't yet, or if you feel you don't really remember much from trig functions. So things to make sure you know is how to evaluate trig functions. Mainly for sure that first quadrant, you've got to know from 0 to pi over 2 what you get when you evaluate that. You need to know cosine of 2 pi, cosine of pi, those main points, but really you never know what you're going to get, so you really need to know how to find trig values of the whole entire unit circle. So make sure that you review that if you haven't done so in a while. And also review your trig identities. We're going to be using a lot of those. So your quotient identities, your reciprocal identities, your Pythagorean identities, as well as the double angle formula. Those are going to be the main identities that we use in this class. So make sure you brush up on those, and let's get into this trig function here. So it's the limit as x approaches pi over 2 of cosine x over cotangent x. And again, direct substitution is the way to go when we're starting out. That's going to be cosine of pi over 2 divided by cotangent of pi over 2. And cosine of pi over 2 is 0, and so is cotangent of pi over 2. So we've got an indeterminate form. That means we need to simplify this. We need to rewrite this somehow. Obviously, we can't factor this. We can't rationalize. We can't combine any common denominators. So our next option, since we have trig functions, is to think of any trig identities that could work to simplify this. So I know that cotangent is equal to cosine over sine. So I'm going to go ahead and replace that. That's going to give me the limit as x approaches pi over 2 of cosine x divided by cosine x over sine x. So I've replaced that cotangent, and now what I can do is I can take the numerator and multiply it by the reciprocal of the denominator, and that's going to be the limit as x goes to pi over 2 of cosine x times sine x over cosine x. And I can already see those cosines are going to cancel out, leaving me with the limit as x goes to pi over 2. Don't forget that limit notation. We haven't done direct substitution yet, of sine x. And now we can try direct substitution. That's going to be sine of pi over 2, which is equal to 1. So we actually could find our limit in this case. Next, we have the graphical technique. So if you look at this problem, again, we can try direct substitution, and that's going to be 1 minus cosine of 3 times 0 divided by 0. And 3 times 0 we know is 0. Cosine of 0 is 1. So again, we have another indeterminate form. What are we going to do from here? Well, we can't factor. We can't rationalize or combine the denominators of fractions that we don't have there. And we can't think of any trig identities. So sometimes when you really get stuck, you really do just need to take that graphical approach. So this is where you'll take out your graphing calculators, or for now, we can also use Desmos and graph out the function. So this is the function 1 minus cosine 3x divided by x. And what we're looking for is the limit as x approaches 0. So I can see here graphically from the left side, we are reaching 0, this point right in the middle here. And then same thing from the right side, we are also approaching 0 right there. So from a graphical approach, I can see that my limit is going to be equal to 0. And that's all there is to it. Sometimes you just gotta graph it out and check to see what's going on graphically. So we know that the limit as x approaches 0, 1 minus cosine 3x over x is equal to 0. And lastly, we have some functions where we need to be able to break down the function and look at the left and the right side of the function because there's different, it's most likely a piecewise function. So we have the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2. Any absolute value function is actually, in fact, a piecewise function. So in this case, the absolute value of x minus 2 is really the breakdown of two functions. It's the positive side, which is just what we have inside the absolute value, and that's going to exist for all the values greater than, not 0, that would be if it was just the absolute value of x. So instead what we do is we take whatever is on the inside and we set that equal to 0 and we solve. So in this case, x minus 2 gives us x equal to 2. So that's the condition. That gives us the condition there for the piecewise. So x has to be greater than 2 when we have the function x minus 2. And then we have the negative side, which is what we have on the inside of the absolute value, but for the negative values. And that's for all values that are less than 2. So now that we've got this piecewise function, and of course we're going to divide it by 2, sorry, not just 2, x minus 2, divide it there. We're going to look for what's happening to the left and the right of the function. And I actually went ahead, I skipped the first part, which is direct substitution. But you can see here, when you do direct substitution, you're going to get 0 in the denominator, as well as 0 in the numerator. So this is 0 over 0, which is why we have to go into this next method. So with piecewise functions, we're always going to have to break down the limit of whatever x value from the left side, and then we're going to have to do the right side as well. And we have to determine, because it's a piecewise function, there's going to be different functions that are taking place on either side, meeting up at that point. So for the left side, I'm going to look at the condition here that shows all the x values that are less than 2, because that means they're to the left of 2. And I'm going to use this function. Now this function, negative x minus 2 divided by x minus 2, is going to simplify to just negative 1. So I'm going to use that here and then be able to just take the limit. So it's nice that it simplifies to just a number here, and we know that the limit of any number is just the number itself. So that's going to equal negative 1 on the left side of 2. And so from the right side of 2, we're going to look at this top equation, and that's what we're going to use to find the limit. And actually, it's the same thing as the last one, x minus 2 divided by x minus 2. That just simplifies to 1. So I'm going to write 1 there, and then our limit of any number is just the number itself. So we've checked the left side and we've checked the right side algebraically, and the numbers don't match up. We have a negative 1 on the left and a positive 1 on the right. So remember, if we're trying to find the total limit, if they don't match up, then the limit does not exist. So for this example here, we've shown that the left and the right do not match up. So the limit of this problem does not exist in this case. Now let's take a look at this last one. We have the limit as x approaches 1 of f of x. And f of x is a piecewise function that we see over here. So when we have the piecewise functions, we're going to break down the limit from the left side and the limit from the right side. And we need to pick which functions correspond with which side. So the left of 1 is all the values that are less than 1, or equal to in this case. So I'm going to use 4 minus x squared as my function here for the left side. For the right side, it's x greater than 1, so I'm going to use 3x. From here, we're just going to find these algebraically, just kind of ignoring that little negative and positive that we see there. We can just go ahead and do direct substitution. So if I plug in 1, I'm going to get 4 minus 1 squared, which is 3. And then if I plug in 1 to the right side equation, I get 3 times 1, which is 3. So this time, the left side is equal to 3, and the right side is equal to 3. So since they are the same on both sides, then my total limit is going to equal 3. So the solution to this problem is 3. And that is all of our limit techniques, or at least the main ones. There's always going to be little ones here and there, little tricks that we'll talk about as they come up, but these are the main approaches, the main techniques that we're going to use throughout the year whenever we are solving limits.